Hello, welcome back to MEC 416/816 Engineering Acoustics. In this lecture, we're going to continue our discussion about single degree freedom oscillators with a focus on forced oscillations. We're going to consider a harmonic oscillator later that is driven by some external force given by f of t here. In this case, our equation of motion becomes mx double dot, that's our mass times acceleration, plus b times x dot, that's the damping force, plus kx, and is now equal to f of t. So I want to point out here that this is the standard form for one of these equations of motion. Everything that has an x on it and its derivatives is put on the left-hand side, and everything that does not have an x involved in it or derivatives is put on the right-hand side. So everything on the right here does not depend on the displacement, velocity, or acceleration. It only depends on time, or it could be a constant if we had a constant force. So f of t can be anything in general. It could be a harmonic force, it could be a random force, it could be a constant force, it can be whatever you want. But in this course, we are going to focus on harmonic forcing only, such that f of t will either be equal to the sine of omega times t, or f of t is equal to a cosine of omega times c. And omega here is an independent variable. It is one that we get to choose typically. It's not related to the structure or the system itself. It's not a property of the system or a parameter. It is something that you get to choose or is supplied by the environment. And in complex form, we can write f over bar of t, where that over bar implies a complex variable. It's equal to that amplitude f times e to the j omega t. So in complex form, our equation of motion is going to become x over bar del m times x over bar double dot plus b x over bar dot plus k x over bar is equal to f of t over bar. In fact, what I meant to write here is actually that complex form. So we will have big F over bar times e to the j omega t. So in general, the general solution for this system is going to include a transient response and a steady state response. So we can write the displacement as being the summation of a transient response plus a steady state response. The transient response is going to die out over time due to the damping, whereas the steady state response is going to continue on for all time due to that applied force. Now the transient response is going to have the same form as equation 22, but the coefficients in front of the sine and cosine terms are going to be different. They're going to depend on the forcing as well as the initial conditions. So in general, when we're studying force response, we're typically interested really in the steady state response. We're not interested in the transient response. We're interested in steady state. And so we're just going to go ahead and solve for that steady state by starting off by producing an ansatz, which again is a German word for an educated guess. And our ansatz is going to be that x over bar of t is equal to some amplitude big X over bar times e to the j omega t. We can then substitute that into our equation of motion, and we'll get the following: minus m times omega squared plus j b omega plus k multiplied by big X e to the j omega t, which is then equal to big F times e to the j omega t. From here, we're going to eliminate e to the j omega t, and then we're going to solve for the complex amplitude big X by dividing by everything in the parentheses on the left-hand side. So we'll end up finding that big X is equal to the quantity big F divided by minus m omega squared plus jb omega plus k. So right now we have the complex amplitude. What we will end up doing is taking absolute value and converting this into a real valued system. And in this case, skipping some of the steps, we can find that our steady state response, a real valued steady state response, is going to be some big X times the sine of omega t minus a phase angle theta, where big X ends up being equal to f divided by omega times the square root of b squared plus the quantity k divided by omega minus m omega squared. And that's our x, and theta here is equal to the inverse tangent of the quantity k divided by omega minus m omega, all that divided by b, and that's our phase angle. Okay, so the complete displacement then is going to be given by the quantity x of t will be equal to, first we're going to have our transient response will be e to the minus beta t plus a times the cosine of omega dt plus b times the sine of omega dt. So you can see this is the same form as what we had previously. I'm going to lower this a little bit. You see that this is the same form as what we had previously, except that the coefficients in front of the sine and cosines are different. So this is again our transient response. This is the response that will die out over time and go to zero. Plus, we'll now have our steady state response, which will be big X times the sine of omega t minus theta, where again here the big X is equal to the quantity f divided by omega times the square root of b squared plus the quantity k divided by omega minus m omega squared. And theta was equal to the tangent, inverse tangent of k over omega minus m omega divided by b. And we're going to add one more note here, is that in order to find a and b, you have to take equation 33 and you've got to match that with the initial conditions. So let's say, note that a and b are computed by matching the initial conditions. Matching the initial conditions with equation 33, meaning that if you have an initial displacement, you've got to set the initial displacement equal to equation 33 for t equals 0. You then have to solve for, you get one equation for a and b, and then you'll have to compute the velocity, and then you'll need to set that equal to initial velocity, and then solve. You'll get two equations, one for a. You have two equations, two unknowns. A and b are your unknowns. You have two equations, one for displacement, one for velocity. You can then solve for a and b, and it is not pretty, and we're not going to use in this class, so we're not going to go through that process. Whenever we deal with force vibrations, at least in this course, and typically when you're studying vibrations in general, this is true, we will only focus on the steady state response. So before we do an example, I just want to briefly sketch what the displacement looks like under forcing. So we'll have time on the horizontal axis, we'll have our displacement x of t on the vertical axis. In this case, we're going to have some initial, let me try that again. So we're going to have some exponential decay in the beginning, and then it's going to level out and become a flat amplitude. Same thing here. And in this case, our displacement is going to look, let's do the full total displacement in blue, and then I'm going to draw part of the steady state in green. So in the beginning here, from say like over here or so, this is our transient response. Well, that is when the transient response exists. And then from then on, for the rest of the response, we're going to have nothing but steady state response. All right, I need a little bit more space here, so I'm just going to shrink this graph. I'm also going to see if I can rotate it a little bit, because I drew it a little bit. I had the iPad at an angle and ended up drawing it at an angle. So that is what our steady state response is going to be: a constant amplitude with it oscillating at a single frequency. All right, we're going to now do an example here. This is our example 3. We're given that a video camera of mass 2 kilograms is mounted on top of a bank building for surveillance. The camera is fixed to the building through an aluminum rod, which has an equivalent linear stiffness of K equals 3 EI divided by L. The wind-induced force acting on the video camera is measured to be as shown there. They then want us to determine the necessary stiffness, assuming zero damping, if the maximum displacement amplitude cannot exceed 0.005 meters. Okay, so this is then now a steady state response kind of question, where in this case we want to determine what that steady state amplitude will be. And it says maximum displacement here. This should really say steady state displacement, maximum steady state displacement. And the reason why we don't care so much about being at a high displacement in the very beginning is due to cycling and fatigue type concerns. You know, hitting a large displacement or a relatively large displacement once may not necessarily damage or break the system, but sustaining that large amplitude for a long period of time can lead to early failures due to fatigue. And so that's what we're really interested in here. Okay, so in this case, we're going to say that our steady state displacement, and that's what it should say in the problem. It should not say maximum displacement. In the video here, in your notes, it will say steady state. So the steady state displacement cannot exceed 0.005 meters. And then they want us to find the stiffness, that the minimum stiffness needed for this to be true, or for it to be less than or equal to this. Once we know that minimum stiffness, we could then actually go back with this equivalent linear stiffness that I'm going to circle right here. We could take that and we could then actually design the support structure of that rod. We could design the length of it. We could design, you know, the thickness of it, the shape, and so forth. We could design that. In this problem, we're just going to solve for that minimum stiffness needed. All right, so what that means is that we need to write out what our steady state displacement amplitude is. That's big X is equal to the force F divided by omega times the square root of b squared plus the quantity K divided by omega minus m omega, that quantity squared. And that must be less than or equal to 0.005 meters. Or 5 millimeters. And we're told to do this on the assumption that the damping is 0. So that then allows us to simplify that displacement, which we'll then have is omega times the square root of the quantity K divided by omega minus m omega quantity squared. Square root of that, we'll get F in the numerator, which then is equal to, we're going to end up canceling out that square root, so we'll get F divided by omega times the quantity K divided by omega, let me rewrite that, omega, minus m omega. We're bringing that omega, and we're going to get K minus m omega squared. So we'll have F divided by K minus m omega squared, and this must be less than or equal to 0.005 meters. All right. Let's call this 0.05. Let's call this big X sub m. That's our maximum displacement. We're just going to use a variable because it's going to save me time in writing this out. It's going to save us time. So what we can do is we can multiply by the denominator, and we'll find that F, the force applied, must be less than or equal to the quantity K minus M omega squared times big X M. We're now going to divide by big X sub M to find that F divided by big X sub M must be less than or equal to K minus M omega squared. We can then bring the M minus the M omega squared onto the other side, put the K here, so K must be greater than or equal to F divided by big X M. In fact, let me move this down a little bit. Let me rewrite that. We're going to have big F divided by X sub M plus M omega squared. So the F divided by X M, that is kind of like a static response in a sense, and then we add some dynamics here through the mass, through that omega squared term. Okay, so we're going to add some numbers here. K must be greater than or equal to, I'm just going to rewrite it first. F divided by big X sub M plus M omega squared. This is then equal to, what was our force? The amplitude was 25. And divided by 0.005 plus, and the mass here was 2 kilograms, right? 2. And that frequency in radians per second is 75.3984. 75.3984. This quantity squared. And if we go ahead and we compute this, we'll end up finding that K, or that value at least, computes out to be 61,369.8, and the units are newtons per meter. So we find that our stiffness must be greater than or equal to 61,369.8 newtons per meter without any kind of safety factor added here. So given this, we could now go ahead and go and design the support structure for this system. Okay, in the next lecture, we're going to cover mechanical resonance, which is very much related to what we just did, and then we'll see what happens under resonance.